Antonio Project presents Chapter 2 Water and Steam Phase Diagram.
Hello everyone! Welcome back to my channel. In this chapter 2 on the water and steam phase diagram, we will discuss one of the most important tools in steam engineering, thermodynamics and power plant operations. Water is a unique substance that can exist as ice, liquid water or steam, depending on its temperature and pressure. Understanding how water changes from one phase to another is essential for engineers who operate boilers, steam turbine, condenser, and other steam systems. In this chapter, we will explore the water and steam phase diagram, learn about the different regions of liquid water, wet steam, dry saturated steam, and superheated steam, and understand how pressure and temperature affect these phase changes. By the end of this chapter, you will be able to interpret the phase diagram and apply it to real-world steam plant operations. Let's begin our journey into the fascinating world of water and steam. Let's go!
This animation shows a simulation of the process of how ice cubes turn into steam. It explains how steam is produced under varying pressures and temperatures. Understanding the differences between entropy and enthalpy is crucial in thermodynamics, as both play essential roles in energy transfer and chemical processes. Entropy refers to the measure of disorder or randomness in a system, while enthalpy relates to the total heat content or energy in a system. The instruments and materials used in this simulation is as follows: kettle, gas stove, ice cubes. The kettle is made of transparent material to make it easier to observe the process change from ice to water and to steam. Ice cubes are stored inside ice cube storage box to maintain the temperature as low as possible. A crane uses to lift ice cubes from storage to kettle. Place the ice cube into the kettle at a temperature of around minus 20 degrees Celsius. Then close the lid. The gas stove is located under the kettle with two burners. The instruments attached to the kettle are as follows. Pressure gauge. It is to measure the pressure inside of the kettle. Temperature gauge. To measure degrees of temperature inside of kettle. Air fan. To release the pressure from kettle to maintain constant pressure. In this case, the air fan is set to open position to release pressure from inside kettle. Safety valve to release excess pressure from kettle. The setting pressure can be adjusted as needed. Initially, the pressure gauge shows 1 atmosphere at a temperature of minus 20 degrees Celsius. Phase change diagram. The following is a graphical representation of the phase change of water at constant pressure, in this case at atmospheric pressure. It illustrates the contents described in phase change diagrams. In many engineering and maritime applications, standard atmospheric pressure at sea level often approximated as 1 atmosphere equal to 1 bar. To make it easier to understand, I will use an animation to show how ice cubes turn into steam when heated inside a transparent kettle. By opening the air vent valve, the kettle's pressure remains constant at 1 atmosphere. In this diagram, the vertical axis or Y shows the temperature in degrees Celsius, and the horizontal axis or X shows the specific enthalpy in kilojoule per kilogram. The phase diagram shows the change of temperature and phase depending on the specific enthalpy contained in the water molecules. Phase 1. Solid phase. The ice cubes heated from minus 20 degrees Celsius to 0 degrees Celsius. In this phase, when heat is added, the ice does not melt or change its physical state. Only its temperature increases. When the heat added or removed that causes a change in temperature of a substance without changing its phase, it calls as sensible heat. The kettle temperature shows 0 degrees Celsius and the pressure is 1 atmosphere on the display. Previously, the temperature was minus 20 degrees Celsius at 1 atmosphere, and the ice did not change from solid ice to water, even though the temperature rose by 20 degrees Celsius. Phase 2. Liquid phase. As ice is continue heated, ice is started to melt and turn to water without change its temperature. The ice slowly melts, turns into water and floats, but the temperatures remain 0 degrees Celsius. The solid ice floats in water because ice is less dense than water under liquid state. When the heat added or removed that causes a change in phase of a substance without changing its temperature, it calls as latent heat. The melting point of ice or the temperature at which ice turns into liquid water is 0 degrees Celsius or 32 degrees Fahrenheit or 273.15 degrees Kelvin. This value applies at standard atmospheric pressure or 1 atmosphere. If pressure changes significantly, the melting point can shift slightly. As water is continually heated from 0 degrees Celsius to its saturation temperature, its condition follows the saturated water line until it has received all of its liquid enthalpy. It's showing on the point C to D. Saturated water is water that exists exactly at the temperature and pressure where it is about to change phase, either to steam or to ice. In most engineering contexts, like boilers, it refers to water that is in equilibrium with its vapor or steam. The saturated water line is the line that represents the condition where water is just about to start boiling or changing from liquid to vapor, usually denoted by HF on steam tables or diagrams. At this point, the kettle temperature shows 100 degrees Celsius and the pressure constant at 1 atmosphere. Phase 3. Steam phase. At atmospheric pressure or 1 atmosphere, water boils at 100 degrees Celsius and 419 kilojoule of energy are required to heat 1 kilogram of water from 0 degrees Celsius to its boiling temperature of 100 degrees Celsius. As the temperature rises and water approaches its boiling point, some molecules gain enough kinetic energy to reach speeds that allow them to momentarily escape from the liquid into the space above the surface before falling back into the liquid. Further heating causes greater excitation, and the number of molecules with enough energy to leave the liquid increases. As water is heated to its boiling point, vapor bubbles form within it and rise to break through the surface. Density of vapor is much lower than that of water because the vapor molecules are farther apart from each other. The space just above the water surface is just filled with less dense vapor molecules. When the number of molecules leaving the surface of liquid is greater than those re-entering, water evaporates freely. At this point, the water has reached its boiling point, or saturation temperature, because it is saturated with heat energy. Due to constant pressure, further addition of heat does not cause the temperature to rise further, but causes the water to form saturated vapor. The temperature of boiling water and saturated steam in the same system is the same, but the heat energy per unit mass is much greater in steam. Coexistence of saturated water and steam refers to a condition where liquid water and steam exist together in equilibrium at the same temperature and pressure. Saturated steam line is the line joining all points where steam exists as dry saturated vapor or no moisture at saturation temperature and pressure. At this point, kettle temperature remains at 100 degrees Celsius and the pressure constant at 1 atmosphere. Dry saturated steam is steam that is at the saturation temperature for its pressure and contain no water droplets. In other words, it is completely dry vapor, just at the point where any heat loss would start condensation. Once it has received all of its enthalpy of evaporation, it reaches the saturated steam line. If continues to be heated after this point, the pressure remains constant, but the temperature of the steam will begin to rise as superheat is imparted. This is shown at point E to F. Heating steam or superheated steam is steam that has been heated to a temperature higher than its saturation or boiling temperature at a given pressure. The characteristics of superheated steam are as follows. Temperature above saturation temperature. Completely dry. It contains no moisture or water droplets. Pressure and temperature are independent. Higher energy content. Lower density or more expanded. Does not condense immediately.
As we conclude this chapter, we have learned how the water and steam phase diagram illustrates the relationship between pressure, temperature, and the different phases of water. The phase diagram is more than just a chart. It is a practical tool that helps engineer predict how water and steam will behave under various operating conditions. Thank you for watching. In the next chapter, we will continue our discussion of steam and thermodynamics. Until then, keep learning and stay curious. See you in the next chapter. Bye bye.
If you think that my video is useful, consider for subscribing my channel. It is win-win benefit for both of us. Thank you for your kind support. Your subscription surely will hit up my channel to steam up.
Thank you for watching my video. Terima kasih. I Antonio Project.